your ratio test notes. But before we get into it, there's one problem here that will require you to know a little bit more about what we call factorials. Now, what exactly are factorials? Factorial is a product of numbers or integers with all the integers below it. Example, 5 factorial. I start by writing it as follow. It's just 5 with an uh, exclamation point next to it. And it actually means 5 times 4 times 3 times 2 times 1. So 5 factorial is the product of all integers starting at 5 all the way to 1. So if I ask you for 4 factorial, it will be 4 times 3 times 2 times 1. If I say 10 factorial, it means we start at 10. That will be 10 times 9 all the way to 1. Now, if I say n factorial, n being an integer, of course, is going to be equal to n times n minus 1, meaning the term before n, times n minus 2, times all the way till whenever you get to n minus n, that will be 1. So it's all the product of all the integers starting from the value given all the way till 1. So what will be n minus 2 factorial over n factorial? N minus 2 over n factorial is the same thing as n. Let's say n plus 2 instead. It's the same thing as n plus 2 times n plus 1 times n and every other numbers below n, so it's just times n factorial over n factorial. And if you simplify here, the n factorials will go away and your final answer is just n plus 2 times n plus 1. This is just a recall. This is something that we will need to know in order to proceed with all the problems on our ratio test notes. One last example about factorial. Factorial, here I can give you a problem, n minus 1 factorial over n factorial. My job is to make these two identical. Well, you cannot turn n minus 1 into n, but you can turn n into n minus 1 because n is actually equal to n factorial is n times n minus 1 factorial. Compared to the top, I can leave it as n minus 1 factorial. After simplifying, I'm left with 1 over n. Then let's now get into our ratio test itself. The first thing you have to know is if an infinite series has a sum, then I can say it is convergence. This is convergent. If an infinite series has a sum, it's convergent. What if it does not have a sum? If it doesn't have a sum, then I would say it is divergent. This is the point of our lesson today, convergent and divergent. When it has a sum, it's convergent. When it doesn't, it is divergent. Let's go with the first example. I'll put 1 here. My series here is 1/4 followed by 1/12. Let me put plus here. 1/4, 1/12, 1/36, and so on. So, first of all, this is called a geometric sequence. I'll put geometric sequence where the common ratio is 1/12 over 1/4 will give you 1/3. The simple fact that I get 1/3, I notice that this is less than 1. I would say it converges. Why? Because for geometric series, when the absolute value of r is less than 1, I will say it converges. When the absolute value of r is greater than 1, this one will be a divergent. Something very important to memorize. So I'll box it for you. That's for geometric. Let's go ahead and deal with another one, this time maybe arithmetic. So for 2, I will give you one such as negative 8 minus 2 plus 4 plus 10 plus and so on. First of all, this is arithmetic. This will be an arithmetic sequence. The common difference for arithmetic, we have a difference, not the ratio. But the common difference here is 6. Now, I would say it diverges. Why do I say it diverges? Because arithmetic sequences will always diverge. Arithmetic always diverge. Let me put the arrows here. Alright, if the series is neither arithmetic or geometric, we use the ratio test. So, this is in case it's geometric, you know that it will converge when the common ratio is less than 1, the absolute value, of course. When the absolute value of a common ratio is greater than 1, you say diverge. When it's arithmetic, it always diverges. When it's not arithmetic or geometric, so not geometric or arithmetic, we use ratio test, and we call it the ratio test. Example, I will say here I have the sum of s of n. If I have that sum of s of n, few scenarios can happen. I would say it converges if the limit at n approaches infinity of the absolute value of s of n plus 1 over s of n is less than 1. It will diverge if the same limit as n approaches infinity of s of n plus 1 over s of n is this time greater than 1. If this limit is the same limit as n approaches infinity of s of n plus 1 over s of n is equal to 1, then this is inconclusive. And when it's inconclusive, we will actually use, when it's inconclusive, you use other test, and that would be in calculus. I would say use other test, and you will learn this in calculus. All right, let's go ahead and jump into a few examples. So the first one, I had 3 already, so let me put example 3. I will say sum as n approaches 0 till infinity of negative 1 to the power of n, 2 to the power of n over n factorial. Well, the first thing you have to do is write s of n. So from here, I will say s of n is equal to negative 1 to the power of n, 2 to the power of n over n factorial. So let's go ahead and go one more step further, and I'll say s of n plus 1 is therefore equal to negative 1 to the power of n plus 1 times 2 to the power of n plus 1 over n plus 1 factorial. Let's go ahead and find the limit as n approaches infinity. So the limit of s of n plus 1 as n approaches infinity. By the way, I found s of n plus 1 because I'm trying to follow this pattern here. It's equal to the absolute value of s of n plus 1 over s of n. That's why I find a sub n and a sub n plus 1. So I will go ahead and find the limit of that. So as n approaches infinity of, it's for all inside the absolute value. I start with the top one, which is, the bottom one, -1 to the power of n plus 1 times 2 to the power of n plus 1 over n plus 1 factorial, that I'm dividing by -1 to the power of n times 2 to the power of n over n factorial. From here, I will use my keep change flip, and it returns that limit to a single fraction now. I have -1 to the power of n plus 1 times 2 to the power of n plus 1. That's my keep. And I have n plus 1 factorial. I just copied the first one, change the second one into, and flip it. It will give you n factorial now on top. And on the bottom, you have -1 to the power of n times 2 to the power of n. This is when your algebra skills will help you a lot. If you use your algebra skill and you simplify, you first need to understand that -1 raised to the power of n plus 1 over -1 raised to the power of n is nothing other than -1. No matter what n is, the answer will always be -1. Likewise, 2 to the power of n plus 1 over 2 to the power of n, no matter what you do, is equal to 2. This is kind of in parentheses so that it will help you understand my next step here. So this is equal to the limit as n approaches infinity. Just like we did for the -1, the -1 will go away, and now I'll be left with just a negative. These values, we try to highlight it. This value and this value are given based on what I have here, and combining these two will give you what I had here. So at the end, your answer will be -2 on top over, on the bottom, I will have n plus 1. And if you don't understand this, how did I simplify the factorial? You need to look again at the beginning of your paper, because I said this n factorial will remain n factorial, and n plus 1 will be n plus 1 times n factorial, and these two will simplify to give you just n plus 1. Keep in mind, it's still inside the absolute value. At this point, I would say this is equal to low over high, y equals 0. So 0 is my answer. And since 0 is my answer, I would say this is less than 1. Therefore, this series is convergent. All right, let's do another one. I know it takes a little time, but it's doable. Let's go on and do now problem number 4. Our fourth example will be the sum as n goes from 0 to infinity of n squared times 3 to the power of n plus 2 over 2 to the power of n. Just like we did previously, the first step is to find an and an plus 1. But I will go straight to and plug in into a limit. Limit at n approaches infinity of, I put my big line, a of n plus 1 would be n plus 1 square times 3 to the power of n plus 1 plus 2 will give me n plus, I have n plus, let's make it 1 here instead of 2. So that is n plus 1 will give me n plus 2 over 2 to the power of n plus 1. Keep, change, flip, the other one will just be 2 to the power of n on top over n squared 3 times 3 to the power of n plus 1. Again, I did the copy, change, flip there. to get to this level. If it makes it easier on you, separate the fraction and put a dot in between. This is equal to the limit as n approaches infinity of, once I simplify, I'll have 3 times n plus 1 squared over 2 to the power of n squared. Looking at this, I feel like you can go ahead and distribute this, but I know that when I multiply n plus 1 by n plus 1, I will have an n squared here. The 3 will multiply the n squared will be n squared and n squared on top. So I will play the coefficient game here, and it would be 3 over 2. Where 3 over 2 is bigger than 1. Therefore, I will say it diverges. Let's look at problem number 5 now. I will do 2 more, and this will end our notes. So I will do number 5 now. For number 5, the sum is, as n goes to 0 to infinity, of -1 to the power of n, square root of n. N is the power of -1. It's not the n's roots. So let me go ahead and remove this. Over n plus 1. Just like I did previously, I will just go straight to the limit as n approaches infinity of -1 to the power of n plus 1 over times the square root of n plus 1 over n plus 2 times, if I flip the other one, I will still have n plus 1 over -1 to the power, -1 square root of n. This is still raised to the power of n. Once again, inside the absolute value. This is the same thing as the limit as n goes to infinity. Now simplifying, I have -1 to the power of n plus 1 over -1 to the power of n. So I will end up on top with n plus 1 square root of n plus 1 over n plus 2 square root of n. -1 to the n plus 1 of and -1 to the n, it would give me just -1, but since it's absolute value, it really doesn't matter. But I'll put a negative there just for you. Well, this limit is equal to, at this point I can tell that they will have the same coefficient. So because the coefficient will be the same, because I see n here, square root of n, square root of n. Same coefficient with no, same degree with no, same degree with same leading coefficient, I will have 1. So since it's 1, I will say test is inconclusive. Let's do one last one. The last one, I'll call that 6. This is the sum. I have sum as n goes to 0, n equals 0 to infinity of n factorial. Let's make it a little bit different. N factorial square over 3n, the whole thing factorial. All right, I'll once again go straight to the limit. That'll be the limit as n goes to infinity of the absolute value of n plus 1 factorial, the whole thing square, over 3 times n plus 1, all inside parentheses factorial, times 3n factorial over n factorial squared. Well, this is equal to the limit as n approaches infinity of, all right, let's go ahead and explain this one. N plus 1 factorial square is the same thing as n plus 1 square times n factorial square that are still multiplied by 3n factorial over 3 times n plus 1 factorial that are multiplied by, not factorial, but times n, 3n, I'm making a small mistake here, times 3n factorial times n factorial squared. From here, I will go ahead and simplify. So if I simplify this and this, this and this, and I have this bottom with this power, I will end up with n plus 1 over 3. That's what it seems to be. The 3n factorial, I simplified it wrong. If you notice what I did wrong, I hope you correct it. But if you didn't, get the right thing now. Once I simplify it all, I'll leave it up to you. I do it for you. You end up with 3n. I simplify it and I'll show you the steps in class. Over n factorial square, which is 3n factorial over n factorial, n factorial. And if you simplify, you end up with low over high, which is 0. This is conversion. I just